It's a bit more technical presentation today. My name is Charly Batista. Uh, I've been working with open source and technology for a few decades now. So I'm currently the president of the PostgreSQL Association in Brazil. And what we're going to talk today is how connections they can impact your database performance. So we're trying to understand a little bit how our database can get better, can get worse, depending on how we deal with connections. And we'll try to address the problem that we might have using those connection things, right? Uh, the world has been changed. So earlier today, Sergey was talking about Kubernetes and those things. And even though some or a lot of people they don't like it, the world has been changed, right? So usually in the past, the technology used to be like long-lived monolith processes. So you're gonna open and create an application, and that's gonna be open and connect to the database and be there forever. So in modern architecture, people are always talking about microservices and how those microservices they are they can die and can be rebuilt, right? So they are not perennial, but they can happen and be rebuilt at the same time. And those things they bring a problem to the database because the database that we use today they've been designed in the old times. The MySQL, the PostgreSQL, and the database that we have today, they are not actually designed and prepared for what we have today. So one thing that we need to understand is every time that you open a connection to the database, that connection is going to use resources on the database, right? Going to use memory, going to use CPU, and going to have an overhead, especially on the startup of the connection. Let's get an example of a Kubernetes application that we have a microservice that maybe have like 50 microservices running on a Kubernetes. So even if that microservices open a persistent connection to the database, what happens if that single service dies and need to be rebuilt by the Kubernetes? Well, that connection that was persistent is going to need to be recreated to the database, right? And every time that the connection is created to the database, we're going to need to have a fork on the database, either a process or a thread. And that's expensive. Those things, they are expensive to the database. And they take time. And in this case, if you have many connections being rebuilt, we can have a storm of the database. And the performance is going to decrease. And let me show you here a short example. I have a database here. This is PostgreSQL, but that happens for any database. MySQL, PostgreSQL, you flavor the name. So what I'm going to do here, I'm going to run this example where it will open 200 connections to my database. And after every transaction, it will close the connection and open again a new connection for the next transaction. So just like the example of the microservice that I gave here. Let's see what happens. So let's wait a little bit for that to start. See, it's doing not bad. It's actually 1,000 transactions per second and 2,000 queries per second, more or less. If I look at my database, this is what's happening to my database. If you see the load average here is starting to increase because, well, it's finished for after 30 seconds. The average here was, where is it? Around less than 1,000 transactions per second and around 2,400 queries per second. Then your database is not that fast. And your developer is going to tell you, look, the application is suffering because the database is not working fast enough. We need more connections to the database because we need to expand and put more microservices because we need to attend that situation, right? So what happened if now we give it 700 connections to the database, to the application? So it was 200 before, and now, as we see here, we have 700. Let's see what happened here, how that database is going to behave. Oops, looks like things didn't go as well as expected. We're going to have a few fluctuation here, but if you go back, now things are going up really faster. What happens here is for every connection that we have on the database, we need to use resources. If you see, I have 14 CPUs here on this machine, on this Docker machine. Using 800, 700 connections, we are way above the number of the CPUs that we have, right? One thing that's going to start going on here is a problem named context switching. The database, the CPU needs to switch from one process to another way too many times in a second. So instead of we have performance improvement, we're actually going to have a performance drop. It was 24 before, and now it's 23. Let's go back here. So we have more connections now, but the performance went down. And what's going to happen is your developer going to call you, man, it didn't help much. We need more connections to the database. And guess what? The more connections you add to the database, the more the performance goes down. Because the CPU doesn't scale. We have the impression that one CPU can do multiple jobs at the same time, but that's not what happens. It's not physically possible. By the laws of physics, it says one body can only occupy the single space at the same time. It's the same process. We cannot have two processes running on the CPU at the same time. What the CPU does is, because it runs so fast that we have the impression that the CPU can do more tasks at the same time. But actually what it does, it gives a small amount of time for each task and switch between of those tasks. Okay, but how can we work? How can we solve the problem? We might have a few solutions in the market today. For example, some languages, they have a connection pooling for that language. For example, Java has this Hikari CP. What it does is, instead of opening 1,000 connections to the database, it will open, let's say, 100 connections, and will circle those connections in the application. So it's not pooling some connections. So we don't send everything to the database. So we circle internally. We also have other solutions like pgbouncer or AJ proxy or other proxies. The problem for those solutions is they don't kind of understand the database language, the database protocol. So they do what we call a naive solution, a naive pooling. So they only pull on the database side. I mean, on the application side. They do not understand how a transaction works. They do not understand if it's a written or write something. And how do you approach this problem? So our solution is we need to build something that actually understands the database. We need to build something that can get the query, get the information from the application, and be able to translate that information from something useful. And this is what the project that we're working now, the decouple, is coming into life. But before we talk about it, let's see what we can do. Remember that 700 connections that was going to the database. Let's run here again, but now we're running against the pool. And let's see how the database is going to behave. Okay, let's wait again to see how that goes. The number of press per second is been increasing. The load on the database is not as high as before. We're going to run again to see how the load was before so we can compare. What happens here is that even though our application is sending 700 connections to the database, one thing that you can look, let me run again, is see the number of processes from PostgreSQL here. This is how many connections we're actually sending to the database. The application is opening 700 connections, but we're sending 14 connections in this example to the database. And even though we're only sending 14 connections to the database, we're processing a lot more queries per second than when we sent those 700 connections to the database. There is a trick here. I didn't show you, but we have more than one database here. We have a cluster. We have a Postgres cluster where we have one primary and two replicas in this case. The proxy here, as I said, it understands the language. So what it does is it sends all the writes to the primary and all the reads to the replica. So in this case, we can bring down, let's run again here directly to the database. See, this is the port, oops, I don't want the dictionary. The port 5432, let's send the connection to the database. See how the load goes up fast. Because now we are sending all the to the database. Let's go to the primary. Look how many connections here our primary has. The tool is even struggling to update because the database is suffering. The machine is suffering with 700 connections to that database. And if you pay attention, the replica is also suffering, even though we're not sending that many connections to the database, to the replica. They're all going to the primary. See here. Because even though we're not sending connections to the replica, all that replication and all that push also goes a little bit to the replica. Another thing that we can do here is we can check what's going on to our database. In this example, we had almost double the number of transactions and queries per second than as we had using the tool, and we are logging all the transactions that we have here. So the architecture that we designed, that we engineered here, we have a few pillars. There are some problems that we wanted to solve that the products in the market today they don't have. The first one is we want to be fully asynchronous. So we use the IO ring primitive that is on modern Linux kernel to do a fully asynchronous IO. So we can save CPU on the proxy itself. We want to be fully prepared for multiplexing even when we're sending a prepared statement. So what is the problem about prepared statement? When you send a prepared statement to the database, or application send a prepared statement to the database, that connection to the database will get an alliance for that prepared statement. And if you try to run on another connection, you're going to have an error because that new connection doesn't know that prepared statement. You need to prepare again. So the proxies, they struggle with those things. There are basically four main techniques. The first one is you don't care if it gets an error, application gets an error. We don't care. The second one is pinning the connection. Every time that your application sends a prepared statement, that connection will be pinned to the application. So you don't have multiplexing that time. Third one that's common is you do a full rewrite to the query. So instead of really sending a prepared statement to the database, you create a table in memory. And when you get that query from the prepared statement, you just append the parameters, the value, and send to the database. And the fourth one is you follow the prepared statement. You are not, again, have a in-memory table. So when you get a prepared statement, you send to the first connection. If you get another one, and if that connection is not available anymore, meaning that you multiplex that connection, you lazily prepare in another new connection. So we basically implement the four of them here, and each application, they might benefit from one another. Another problem that we have here is, let's go this one. This is funny here. A read after write inconsistency. A problem that we have when we have a primary and a few replicas is, imagine you have a bank application, a user go there and does a withdraw money. Because it's a writing application that goes to the primary, right? So I withdraw my money. If I want to check how much money I still have, my balance, and if the connection goes to the replica immediately, I'm going to have a consistency issue. Because the write that went to the replica very likely was not propagated to the primary, very likely was not propagated to the replica yet. Or if you have a replication lag, a time replication lag, you still have a consistency issue. A lot of applications, they solve this on the application side. They have a really complex logic to solve that on the application side. So what we do is, when we have a write, we follow the transaction log, LSN transaction log. And if we get a select that will eventually go to a replica, and it's getting that, asking for that specific information, so that select will be kept waiting until the next replica it gets been updated. When that LSN gets to the replica, it means, okay, yeah, that was propagated, and then it goes back to the application. So your application doesn't crash. It has a delay, obviously, but that's consistency. So if you need to have hard consistency on your application, that's the trade-off. You're going to increase the latency a little bit because your replica will have a latency to update, but that's going to be consistent. So the correctness under multiplexing. A lot of people, they believe when they are using synchronous replication, they're solving all their problems, including this problem that I mentioned. But imagine this situation that you're doing the same problem. You're doing the withdrawal from the bank. It goes to the primary. Because we're using a synchronous replication, the primary will wait for the replica to apply that data, that transaction, before sent to the client, right? So the transaction goes from the primary to the replica. When it gets to the replica, it's been applied. The replica will notify the primary, and then the primary will notify the application. Imagine that after the primary gets notified by the replica, the primary crashes. The application will receive an error because the primary crashed, but that was already drawn from the bank account because the information is in the replica, and the replica is going to be promoted. That replica is going to be the new primary. The application will try to redo the transaction. If it's idempotent, that's okay, but most of the applications, they are not. Most of the application designs, they don't think that those problems might happen. So what's going to happen is you're going to have a now consistency issue. So we have a probe for the commit in doubt recovery. If a problem like that happens and we follow the transaction and we know that the transaction was applied, we notify the application. So those are few designs that things didn't used to happen that in past, because when the databases were designed, those were not the problems. And we try to design those in that way. Another thing that we think it's really useful and it's nice to have is we have hooks. So you can hook on your application. Remember that I showed you here these nice logs. This log here is for everything that happened on the database. Let's see this is the log from the proxy. I have here a database connection. Let me see if I'm on the primary. No, I'm on the replica. I'm going to connect to the primary. Let me see what are the tables that we have. No, that's not happen. I need to connect actually to the proxy. Is 127.0.0.1. The port is 7432. Okay, I'm connected to the proxy. Let me see what the tables that we have. So, whoops, I didn't copy. I'm just going to get whatever table that I have here, see? And I'm going to do a drop table, which is pretty bad. This table here. I copied something else. Let me copy again. SB test 1. Drop table. This. Let's make it easier. Create table T1 ID int. All right, now we can drop this table. Drop table T1. See, that's hanging here. We don't have any data on that table. Why is this hanging here? Why is it taking so long? Well, if we go here, we'll see that a hook, it's blocked the drop statement from happen on my database. But why does hook block this statement? Well, because I created a hook here. Let's go for examples, hooks. Let's go for the Python one. That is the dangerous here. So I created this hook where everything that is in the proxy get exposed, including the SQL tree, because we pass those statements into a tree. And here I'm checking, oh, is this statement a drop? Well, if it's drop, this statement being blocked. Oh, is this a delete without where? Oh, if it's a delete without where, I've been blocked. So actually, we can do whatever we want before that gets to the database. In my case here, I didn't return anything because I wanted to keep in the example that was easy to see that it was blocked. But you can return an error for the application. Look, oh, what happens if I have a specific user that I want to have very specific type of access for a specific database or set of tables or records or whatever? Oh no, I don't want to log all the selects because that's going to be very expensive because we're writing all the selects here. I want to log a specific type of selects. Well, do you write Python? Do you write Lua? The sky's the limit. You can do whatever you want. So those are the features that we believed are very valuable, and they not only give power, but we can also get, as we saw, performance improvement. Because we're shifting the load from the database to a proxy, and because we can split that load with multiple databases, so we also have a huge performance improvement, a huge performance gain. And the last thing is it's plugin based. So we work with protocols. And for example, if we go for the configuration here, let me make it larger. Now we are working with PostgreSQL. We can have on the same binary, on the same port here, a MySQL one. So the same proxy that you can use with your PostgreSQL application, with the hooks and everything, you can use with your MySQL database. Oh, but if I use MongoDB, well, it's plugin based. You just need to write another plugin. Oh, if I use whatever, let's say I want to have something spectacular here and you use with Oracle. Well, if one is eager enough to write an Oracle plugin, let it be. So, and that's the main idea for this guy. Oops, not this. Is to give you freedom, to let you do whatever you need to do, and to shift some of the responsibilities that you have from your application, some of complexities that you need to put on your application today, or some complexities that you need to put on your database. Maybe you have a lot of user-defined functions on your database to define some specific access rules or queries rules that is slowing down everybody on the database, or you have those complex rules on the application. Well, you don't need to have them there. You might just shift them to the proxy layer. We're still in development. Our hope is to be in beta in around June, July. So, as soon as we have stable enough code, because now we have too many bugs, we're gonna release as a fully open source software. And that's it. If you have questions, no, that's open source fully. Thanks, everybody.